Welcome to the first video in Unit 7. We're going to do a graphing review of exponentials, and we're going to solve some exponential equations without logarithms. Here are the objectives here. And so let's get started. Exponential equations are in the form y equals ab to the x power, where a is the initial value and b is the base. So if it doubles, for instance, this would be a 2, and then you have an exponent, 2 to the exponent. B is a number, a is a number. If a is just 1, of course it's going to start at 1, and it would be a true basic exponential function. So looking at this function that's given here, it says f of x equals 5 times 2 to the x. So we know that 5 is the initial value, and we also know that 2 is the base. So if we were going to graph this function very quickly, we could make a little table, and we would say, let's say negative 2, right? And we would say 2 to the negative 2 power is 1/4, so that would be 5/4. Negative 1, that would be 5/2. 0, well, anything to the 0 power is just 1, so that would be 5. If I put a 1 here, 2 to the first times 5 is 10. Okay, so it should make sense that the initial value is 5, so at 0 the value is 5, and then over 1 goes up 10, right? So this is a growth function. And then as it gets closer and closer down to the x-axis, it's going to run into the asymptote. So it looks like this. So what does 5 do to the graph? Well, it looks like it is a stretch. Okay, so I'm going to write in y equals 0. That's my asymptote for this equation. But the 5 is where it's going to cross the y-axis. So we can apply transformations to the exponential function. Okay, and so when you look at something like this one right here, you would see that the parent function is going to be y equals 4 to the x power, and that's going to be true for both of these. And then on this first one, where I have it underlined in blue, we know that the minus 2 at the top moves the equation to the right 2. The plus 3 moves it down 3. Okay, so the 2 is with the exponent. So over here we have the parent function is going to be y equals 1/2 to the x power. This one was growth. This is decay. All right, so that's our parent function. Decay. Okay, and then the minus out in front is reflected over the x-axis. The minus 1 is to the right, 1, and the plus 2 is down, up 2. So all those same transformations can be used with exponential functions. So every once in a while I need to throw in a story problem. It just says that the number of bees in a hive is growing exponentially at a rate of 40% per day. The hive begins with 25 bees. Which function models the population of the hive after t days? Okay, so we'll start with the t days, right? That would be the exponent, which if you're looking at a, b, c, and d, they all have an exponent of t. And so that would be the t days. Then it says you begin with 25 bees. So I look here, this begins with 1, this begins with 1, these two begin with 25, all right? So then you have to decide if it's growing at a rate of 40% per day. We remember that that would be 1 plus 0.40, and so that would be a growth rate of 1.40. So remember, we're always adding to it. Since it's growth, right, then we would do 1 plus. If it was decay, we'd do 1 minus. So it has to be A. So here's an interesting thing. If you wanted to tell, just by looking at a table, if a function is linear, quadratic, or exponential, there's a way to do it. And so let's look at this first table. This is a linear function. It says that the output difference is a constant. So you can see that, also the input values must be evenly spaced. So notice it's 1, 2, 3, 4, 5, 6, 7. There's nothing missing, nothing missing. So as you look at the output, they're always going to be 2 apart. And that makes sense if you think about what the slope is, right? Because you go over 1, up 2, over 1, up 2. And so as they go over 1, it's going up 2. Okay? So that would be a linear function. Now in a quadratic, it won't start being the same number until the second time you go through it, which kind of makes sense because quadratic is something to the second power. So the first difference will be linear, but the second difference will be a constant. So that's what you're after, is you're looking for the difference to be a constant. So I look here, and this is 6. The difference here is 10, then 14, then 18, then 22, right? That's always 4 apart. Okay, and so the differences here are 4 apart. So 6 to 10, 10 to 14, these are all 4 apart. Then this would be a quadratic function. Now, for exponential function, the output ratios are constant. So in other words, if you took 6 divided by 3, that would be 2. 12 divided by 6 is 2. 14 divided by 12 is 2. 48 divided by 24, and so on and so forth. Then the difference, the ratio would be a constant value. Okay, so this is how you can tell from a table. So let's try one over here. We have on the next screen. Okay, so in table A, we notice first that everything is evenly spaced. We've got evenly spaced tables, right? So then here we see that 5 to 6 is a 1, 6 to 9 is a 3, this is 5, and this is 7. And then when we try it again, this is 2, 2, and 2. So since it's the secondary one, this one is quadratic. All right? Over here we have, first thing we want to try, this is 8. Try this again. This is 8, this is 8, and this is 8. So B is linear, right? It has a slope of 8. All right, so over here what we have is 10 over 5 is 2, 20 over 10 is 2, 40 over 20 is 2, and 80 over 40 is 2. This is exponential. Okay, not very hard, but it's kind of interesting to see. The x values have to be evenly spaced for this to work. Okay, so we're going to tackle something a little bit different this time. Now we're going to look at exponential numbers, and we're going to rewrite them in a certain way. So we have 9 squared, right? So 9 squared is the same thing as 3 squared squared. So that would make that 3 to the 4th power. And of course you can verify that numerically. All right, so 16 squared then, 16 is 4 squared, right? And then 4 is 2 squared. So this would be 4 to the 4th, and this one would be 2 to the 8th is 16. Actually, 16 squared, which is 256, which can also be verified numerically. So we can use those patterns and rewriting of exponential functions to actually solve. So we see here that 3 to the x is equal to 9 to the 4th, and we want to know what the x would be. So I'm going to rewrite 3 to the x is equal to something to the 4th, so this would be 9 is 3 squared, so 3 to the x equals 3 to the 8th, and because these bases are the same, then we can also say that the exponents are the same, and so x would equal 8, which you could verify on a calculator. Okay, so we can get even more complicated. This second one over here says 2 to the 5x is equal to, and the key to this is to get the same base. So I'm going to rewrite the 4. I'm just going to put that right there. I'm going to rewrite the 4 as 2 to the 2nd power. And so this would be 2 to the 5x equals 2 to the 2. I'm going to do 2 times both of those. So this would be 4x minus 2. Well, because these are the same, I can say that the exponents equal each other. So x is going to equal -2. And that would be your answer. So it's pretty simple once you know how to rewrite it. And the property that allows us to rewrite it is called the one-to-one property. And that just says that if I have 3 to the x equal 3 to the x, if the bases are the same, then the exponents have to be the same. So that's the property that we're using here. Next, we have 4 to the 2x plus 3 power equal to 1. Now you remember that anything to the 0 power is equal to 1, so we could rewrite it this way. We could say 4 to the 2x plus 3 equals 4 to the 0 power. Well, now the bases are the same, and we would say 2x plus 3 equals 0, 2x equals negative 3, and x equals negative 3 halves. Right? If we do the same thing over here, we want to know what 243 is to what power. And one way you could do that, since that it needs to be to the third power, right? So I would divide that through by 3. And so 3 goes into 24 8 times, so 81. And then this is 9 and 9, which is going to be 3, 3, 3, 3. So just count the 3s. There's 5 of them. So I know 3 to the 1 minus 2x equals 3 to the 5th. And now if these bases are the same, we can say 1 minus 2x equals 5. Negative 2x equals positive 4. And so x is equal to negative 2. And that's how that works. And if you put negative 2 back in there, you get 1 plus 4, which is 5, 3 to the 5th, which is what 243 is. So you can check by plugging it back in. So finally, we'd like to look here at a table of values, and they're written horizontally instead of vertically this time. But perhaps we can kind of see which type of equation best models the data in this table. Well, we know it's not linear because it's not a constant, both from each one of these, right? So this would be 4 and 2 and 1 and 1/2 and whatever. But we can see that 8 divided by 4, negative 8 divided by negative 4 is negative 2. Sorry, positive 2. This one's positive 2, this is positive 2, this is positive 2, all the way down. So we know that this is exponential. So we've gone over a lot of things in this one video. We've gone over the transformations, we've reviewed tables and how you can tell if they're linear, quadratic, or exponential. We have graphed an exponential, looking at a stretch at the very beginning. We have solved exponential equations without using logs. We've used the one-to-one property. They have to be the same base. And then we've looked at another table in here. So there's quite a lot. We'll come to class, and as always, we'll spend the hour practicing all of these concepts. So I hope you took good notes, and I'll see you in class.